So if you've been following the software world at all lately, I mean, it's impossible to miss.
Oh, absolutely. It's everywhere.
Large language models.
Mhm.
You know, they're not just writing little functions or um, summarizing articles anymore. They've really evolved into like active collaborators.
Right.
We're seeing these software engineering agents, things like Deep SWE or Code World Model CWM, and they are, I mean, they are dramatically boosting developer productivity.
They're part of the team now. They can take on complex GitHub issues. They can draft pretty sophisticated pull requests.
Mm.
It makes life a lot easier for programmers.
It really does. But, you know, for all the hype, there seems to be this ceiling we keep hitting.
A fundamental barrier, yeah. It's a technical and a financial ceiling, really. All of these impressive agents, I mean, even the really advanced ones using reinforcement learning to get better, they all rely critically, and I mean critically, on human knowledge.
Okay, so when you say human knowledge, you mean they're trained on these just mountains of curated data, like millions of GitHub issues, pull requests written by people, and test cases that a human developer sat down and meticulously defined.
Exactly. They are exceptional students, but they're still mimics. They are experts in the specific style, the specific flavor of software engineering that humans have already done.
So they're good at playing our game.
They're great at playing our game. But that dependence on human traces, it limits not just their performance, but their scalability. Collecting that data is hard, it's incredibly expensive, and, maybe most importantly, it stops these agents from independently discovering entirely new classes of problems.
Or pioneering new solutions that no human has even thought of yet.
Precisely. They are essentially trapped in this cycle of replaying and refining the development history that we created for them.
And if we want to get to what some researchers are calling superintelligence in software engineering, I mean, a system that can design and debug at a level that just completely exceeds human capability, that whole data model has to break.
It has to. It's a huge pivot.
It seems like if the AI is limited by the curriculum that we write for it, then the only way to get a true breakthrough is, well, to let the AI write its own curriculum. Okay, let's unpack this.
Yeah, that's exactly where we're going.
Right.
Today, we are diving deep into a new training paradigm called self-play, SWE-RL, or just SSR.
SSR. And this is being positioned as the breakthrough that's designed to shatter that human data ceiling.
That's the goal.
The mission of SSR, at least as it's laid out in the research paper we're looking at, it sounds revolutionary. It's to create agents that assume the absolute minimal data input, basically just sandbox repositories with source code, dependencies, and nothing else.
Right, no user manual.
No user manual, and from that, achieve this rapid, almost exponential self-improvement.
That's right. The ultimate goal, as the paper argues, is to create systems that can autonomously gather these vast, diverse learning experiences and eventually enable truly superintelligent systems that exceed our capabilities, not just mimic them.
So our source material for this deep dive is that technical paper. It details the whole SSR architecture. It gives us the blueprint for this self-training process. We're going to get into its fascinating mechanisms, its internal adversarial components, and see how it really stacks up against relying on all that costly, unreliable human data.
This isn't just about an optimization, as you said. This is about cutting the umbilical cord to human knowledge in software development.
Let's do it.
Yeah.
We hear so much about scaling LLMs by just, throwing more data at the problem. But in software engineering, what this SSR paper really highlights is that data isn't just scarce, it's often fundamentally problematic.
Yes.
It's not a scaling problem. It's more like a reliability crisis.
It absolutely is. It comes down to trustworthiness and cost. When you try to train a model on a massive scrape of public GitHub repositories, you are making huge and often very faulty assumptions.
Like what?
Well, you're assuming the user described the issue correctly. You're assuming the development environment was even reproducible. And you're assuming the fix that was committed actually solved the problem it claimed to solve.
Without, introducing 5 new bugs in the process.
Exactly. Every single developer listening right now has opened a bug report that says something vague like, the checkout button breaks randomly.
Right. And then you dig in, and it turns out to be this 3-way race condition that involves some obscure dependency, a cloud API that's timing out, and an outdated version of a Python library.
Precisely. That kind of real-world noise and ambiguity, it's just terrible for structured, reliable machine learning. It's poison for training a robust agent.
So the process of gathering high-quality, actually executable training data is not just hard, It's fragile.
And expensive. You have to make sure the environment is reproducible down to the exact commit hash, that all the right dependencies are installed, and that the tests provided are actually valid representations of the bug in the first place.
And the researchers behind SSR, they quantify this difficulty, right? They point to the need for these very specific, manually curated data sets.
Yes, exactly. The difficulty is just proven by the very existence of benchmarks like SWE-bench Verified. The fact that researchers had to go and create a subset of the original SWE-bench tasks that were human verified.
So a person had to actually go in, reproduce the bug, apply the fix, and then confirm that it worked.
Yes. That speaks volumes. Without that extensive, costly human inspection, the curated training signals are often just unreliable, or worse, they're not even executable. They don't run.
Okay, so if the foundation, the data is shaky, then the agents you build on top of that shaky foundation are also going to be shaky.
They have to be.
The agents become these excellent imitators. They get really good at refining existing human knowledge, but they're not truly inventive. They can't discover a new class of semantic error, like a deadlock in some novel threading paradigm, if all they've ever seen are the classes of errors that humans have already defined and fixed.
That is the core limitation of imitation learning in this domain. And this is exactly where the AI research community starts looking to other fields where self-play has historically created superhuman intelligence.
Right, you're talking about the classics, the systems that completely redefine their fields.
AlphaGo,
Yeah.
AlphaZero, exactly. Those systems achieved superhuman play using self-play in domains defined by fixed, unchanging rules. Go, chess, shogi.
Simple closed domains.
In those closed domains, you give the AI the rules of the game, and it just plays against itself millions and millions of times, exploring the possibility space until it finds these optimal strategies that just far exceed any human intuition.
But software engineering is not chess. The rules are not fixed on a 19 by 19 board. It's this chaotic, open domain with evolving dependencies, legacy code, and complex human intent layered on top.
Right. And there have been valiant attempts to bring that self-play idea to more open, generalized domains. You see things like Absolute Zero or R0. These systems often rely on pure LLM introspection.
Okay, what does that mean? Introspection.
It means the model proposes problems to itself, solves them using its own internal knowledge, and then learns from that process. It's all happening inside the model's head, so to speak.
Wait, let me make sure I understand the critical difference here. If an LLM is purely introspective, like in those systems, it might propose a coding task and solve it internally. Maybe it runs a few snippets against a simple Python interpreter. What's the inherent limitation when it's only talking to itself?
The limitation is a concept called grounding. While an agent operating purely on introspection can learn all the intricacies of, say, Python language semantics, it cannot acquire and I'm quoting the paper here, the much greater knowledge and experiences contained in real-world codebases.
That makes perfect sense. Okay, think of it like a human developer who only ever reads the official Python language specification document and uses the interpreter. They might know every single corner of the language, every obscure feature.
A true language lawyer.
A true language lawyer, but they still won't know how to navigate the complex folder structure of a real project, or handle conflicting dependency graphs, or figure out the specific build commands for, I don't know, a decade-old Flask web framework.
Exactly. That knowledge is external to the language itself. It's the messy reality of engineering.
And that inability to ground the self-play in a complex, real environment really frames the need for SSR.
Yes. SSR is designed specifically to ground its self-play in these huge, messy, real-world repositories. It forces the agent to learn the actual reality of software engineering, the weird build commands, the strange test suite structures, the legacy code, not just the abstract rules of the language.
So the mission fundamentally shifts. It's not about feeding the agent more human solutions. It's about giving it a sandbox full of real code, cutting it off from all that external knowledge and just telling it, go figure out how to be an engineer in here by making your own challenges and solving them.
Okay, so the core challenge is taking this concept of adversarial self-play, two AlphaGo policies, battling it out, and translating that into the chaotic, multi-layered world of a software repository.
It's a huge translation problem.
Which brings us to the core innovation of SSR, the architecture of this internal conflict. So how do they formalize the fight?
The SSR architecture is Highly structured and very specific. It uses a single large language model policy.
Meaning the weights of the model are entirely shared.
Entirely shared. But that one policy is instantiated into two distinct roles, and it does this through strategic prompting. On one side, you have the bug injection agent, which acts as the challenger.
It's the agent that breaks things.
And on the other side, you have the bug-solving agent, which is the solver. So it's essentially one brain talking to itself. But it's wearing two very different hats. One is this chaotic, destructive hat that breaks things in really subtle ways, and the other is the diligent, methodical one that has to come in and fix them.
Exactly. And they're trained jointly using reinforcement learning signals that come directly from their interaction. And I really want to stress this minimal input assumption again. The agent gets only a pre-built Docker image of the repository.
So it has the source code, the dependencies are installed.
But that's it, nothing else. The agent has to discover the test runner, the test structure, the project's weird conventions, the language intricacies, all on its own through just interacting with the environment.
And that's the huge difference from the human data baseline, right?
Okay.
That baseline gets the exact test command and a detailed issue description handed to it on a silver platter.
Correct. SSR has to generate all of that necessary context first.
Let's start with the challenger role then. The bug injection agent. What's its primary job beyond just, breaking code?
Its task is really threefold. It has to explore the code base, figure out how things work, and then produce a formal bug artifact.
A formal artifact.
Yes, and this is absolutely critical because it eliminates the ambiguity that's inherent in all those natural language issue descriptions. We already established GitHub issues can be vague, they can be misleading. SSR just completely sidesteps that noise.
A formal artifact sounds highly specific, very structured. Let's slow down here. What are the 5 essential components that the challenger is forced to generate? What does each one do?
Okay, so the bug artifact has to contain these 5 crucial components for the system to validate it and use it. Let's walk through them.
Please do.
First, you've got testscript.esh. This is the bash script that the agent figures out, often through trial and error, that actually runs the test suite in this specific environment.
This is the essential start button for all the testing.
Exactly. Second, testfiles.txt. This is just a manifest, a list of the original pristine test files. This is important because the system needs to know which files have to be reset later to ensure the evaluation is fair.
A ground truth.
A ground truth. Third, and this is maybe the most crucial part for the learning loop, is testparser.py. This is a Python script that the agent itself has to write.
It writes a script.
It writes a script to parse the raw, messy test output, all those verbose lines you see in the console, into clean, structured JSON results. This structured data is the only way the AI can reliably quantify its own success and generate verifiable RL rewards.
Wow. Okay, so those first 3 pieces basically establish the functional environment, they define what correct looks like, and they provide the internal scoring mechanism.
You got it.
Now for the 2 pieces that actually define the bug itself.
Right. So fourth is buginject.diff, which is just a standard Git-style patch. This is what introduces the actual bug into the source code files. This is the act of breakage.
Simple enough.
And then the 5th piece is the most innovative part, I think. It's the core of the self-play mechanism, .testweaken.diff. This is another patch, but this one modifies the test files to intentionally remove or weaken assertions.
Okay, wait. The challenger is trying to find a test gap, a hole in the safety net that lets the bug it just created slip past the test suite.
That's it, exactly.
Here's where it gets really interesting for me. Why does it have to introduce a test gap? If the goal is to find difficult bugs, why make them harder to spot?
Well, it simulates realism in a couple of ways. First, real bugs often do slip past existing test suites, so it's just a more realistic kind of challenge. But second, and this is the most important part for the training loop, the reversal of that weakening patch.
The testweaken.diff file, but inverted.
Yes, which the research docs call the Oracle dispatch.diff. That reversed patch acts as the precise formal specification for the solver agent.
Ah, I see. So the reversal of the weakened tests become the explicit demand on the solver. It's basically saying, you must make these exact tests pass the ones that I just weakened to hide my bug.
Exactly. That formal specification is orders of magnitude less ambiguous than any natural language issue, like the user reported an error when calculating averages. The bug injection agent is forced to learn not just how to break code, but how to write an excellent, unambiguous specification for the fix, grounded in verifiable tests.
So the bug injection agent has to be smart enough to A, break the code, and B, remove the guardrails that would normally catch that break. And the inverse of those removed guardrails becomes the objective for the fixer. That's an ingenious way to generate a formal curriculum.
Is.
So how does the challenger make sure the bugs it creates are actually complex and diverse, instead of just trivial one-line errors over and over?
They adopted 2 successful generation strategies, and they guide the challenger agent towards them using prompting. The first one is called the removal-oriented bug. This involves instructing the agent to just delete entire code files, or at least substantial hunks of code. The agent is then required to perform compatibility fixes to make sure the project still runs. It can't just break compilation, but the core functionality is gone.
So it forces the solver to reconstruct that functionality from scratch. That deepens its understanding of the codebase's structure and all its dependencies.
Right. It's a much more sophisticated challenge. It's like removing a key structural support from a building and saying, now put it back, but the structure has to remain standing while you work. It forces the solver to do architectural reconstruction, not just small tweaks.
Okay, and the second strategy?
The second strategy is the history-aware bug. Here, the challenger selectively reverts past code changes from the repository's own Git history. For example, it might find and undo a past bug fix or revert a recent performance optimization.
Oh, that's clever. That creates more realistic semantic bugs errors that genuinely existed in the codebase at one point in time. It gives the self-play loop a flavor of real-world regression testing.
It does. And they also mentioned something called consistency validation checks, right? This is the system making sure the challenger isn't cheating by creating easy homework for itself.
Yes. Before any bug artifact is considered valid, it has to go through these rigorous consistency checks. They make sure a minimum number of files were changed, a minimum number of tests are now failing, and importantly, they use something called inverse mutation testing.
Wait, hold on. Let me make sure I understand that. We hear about mutation testing all the time. That usually measures the quality of the test suite by trying to introduce small bugs and seeing if the tests can catch them.
Right.
How does the inverse work here? What are they measuring?
The inverse approach measures the quality of the bug itself. It verifies that every single file modified by that bug injection patch is actually necessary to trigger the failure. It checks it by one, reverting just one file back to its original state. If reverting that file causes a failing test to suddenly pass, then that file definitely contributed to the bug. But if reverting a file changes nothing, that file was just an orphan modification and the whole artifact fails the consistency check.
Wow. That is highly detailed engineering. It's all designed to prevent the AI from just padding the changes or giving itself an easy pass.
That process alone is incredible. It forces the challenger to be precise and purposeful in its destruction. Okay, so now let's turn to the second role, the solver agent. The challenger has engineered this magnificent trap complex, hidden bug, with a known oracle. How is the solver prevented from immediately detecting that trap?
That's a crucial structural constraint. So the solver receives the environment with both patches already applied, the booginject.diff and the testweaken.diff. But critically, before the solver can even start work, the repository is immediately reinitialized. They run rm-r.git and create a fresh commit with just the buggy state.
Wait, okay, let me push back on that a bit. If the whole point is grounding the agent in real code bases, but then the researchers immediately remove the Git history, doesn't that make the environment less realistic for the solver? I mean, how can a human developer track changes without history?
That is precisely the dilemma, but it's a necessary trade-off. They have to do it to maintain the integrity of the learning loop. If the agent could just inspect the Git history, it would instantly know what was changed and where to put the fix.
Right, that's Git leakage, the ultimate cheating loophole.
It's the ultimate cheat. By removing the history, they force the solver to operate like a developer would when faced with a broken production system. You have to analyze the code from scratch without any immediate insight into what caused it. You have to rely on your learned skills in semantic analysis and debugging, not just history inspection.
That makes sense. It focuses the training on true debugging capability. And the prompt it receives is that formal reverse test weakening patch, the explicit requirement of which tests it must make pass. So what happens when the solver produces its fix? How do they validate that against the challenger's sneaky attempt to weaken the tests?
The validation process is extremely strict to maintain integrity. The pipeline first tags the original pristine codebase state as original. The solver's predicted patch is applied to the buggy, weakened codebase. Then, and this is the key, the test files themselves are restored to their pristine original state using that store original tag before the tests are run.
So it guarantees the solver didn't just game the weekend test. It has to pass the full original Oracle test to be considered successful.
Yes, the agent has to demonstrate genuine functional repair.
It's a beautifully closed, self-contained, and highly adversarial feedback loop. The challenger tries to create a difficult, hidden, complex bug, and the solver has to reconstruct the functionality to satisfy the original unweakened safety requirements. It's just brilliant.
Yeah.
One of the biggest goals of SSR isn't just creating one difficult bug, but generating a continuously evolving curriculum. You don't want the agent solving the same type of simple problem over and over, because then its learning just plateaus.
Right, you hit a local minimum.
So how does this system ensure the problems keep getting harder and more structurally diverse?
This is achieved through the integration of something they call higher-order bugs. And this is where the training loop gets incredibly efficient. When the solver agent fails an initial repair attempt, let's say it introduces a typo while trying to fix a threading issue, that failed attempt, the resulting buggy code state, is captured and recycled.
It's recycled.
Yes. This new failure-derived state is then used to form a higher-order bug for the next training iteration.
So wait, the agent's own mistakes become the training data for the next round. And they're specifically targeting the vulnerabilities that were exposed by its own failed repairs.
Exactly. It perfectly mimics how real developers work. I mean, how many times have you fixed one bug, and in doing so, you inadvertently introduce another one?
All the time.
Or your solution conflicts with some other functionality because you didn't fully understand the side effects. These higher-order bugs, they expose the system to these layered, interdependent failure patterns. It resembles the multi-step edits that you need in natural software development. It enriches the training data far beyond just a simple single-line dilution.
So it learns from its typos and its poor architectural choices.
Right.
That's a highly efficient feedback mechanism. It's always learning at the absolute limit of its current skill. Now, let's talk about the engine that's driving this whole conflict, the rewards. At the core is an adversarial reward system that's designed to push both agents toward the optimal frontier of their skill.
Right. The goals of the two agents are explicitly opposed. It creates an arms race. The solver's goal is very simple. Maximize the success rate, which we'll call C dollars. It gets a straightforward binary reward, +1 for success, -1 otherwise.
Easy enough.
The injector's goal, however, is much more complex. It wants to maximize challenge, but crucially, it has to maintain solvability.
And that sounds like that tightrope walk we talked about.
Yeah.
You want the problem to be hard, but if it's literally impossible, the solver learns nothing, and so the injector should be penalized for that.
That's precisely the sweet spot the researchers had to engineer. The injector is heavily penalized if the solve rate zero-way, meaning the bug is just too hard for the current solver policy, and that results in wasted effort.
Okay.
It's also penalized if CD dollars is 1, meaning the bug was trivially easy, which is just redundant effort. The injector's optimal reward is achieved when the solve rate is somewhere between 0 and 1. Ideally, they target a low but non-zero success rate, maybe around 20 or 30%.
So how do the researchers calibrate that reward function to make sure the system doesn't just collapse into the easier states of CZs being 0 or 1?
This reward structure forces the challenger to continually target the frontier of the solver's capability. Let's say the solver gets better and it starts solving 50% of the current batch of bugs.
Right.
The injector's reward drops, and that forces it to immediately find structurally harder bugs to maximize its own score. This guarantees an evolving and maximally informative curriculum. The injector is constantly forced to walk this tightrope, knowing that if it fails, it risks giving the solver a free pass, or even worse, creating an unlearnable mess.
It's a continuous self-calibrating arms race based on the shared policy's current skill level. But the research team introduced a fascinating theoretical vulnerability here, something they call the dominant challenger strategy. What is that, and why is it so dangerous for these kinds of self-play systems?
This is a really deep theoretical insight, and it applies whenever an AI agent has a vast or even Turing-complete action space, which a software agent essentially does. The paper points out that a sufficiently intelligent challenger could find these dominant strategies, basically cheat codes, that maximize its reward without providing any useful training signal to the solver.
Okay, give me an example of that. How might a theoretical super challenger cheat the system in a way that doesn't actually require it to generate a complicated bug.
Okay, so the challenger could create a test that fails pseudo-randomly based on a hash of the current code.
Oh, wow.
The solver can't reliably predict the outcome or find a deterministic fix because the failure is effectively random. But the challenger still gets a low score and therefore a high reward for creating what looks like a hard problem.
That's devious.
Another strategy, even more malicious, would be for the challenger to just obfuscate the entire codebase. Fill it with junk comments, meaningless variables, make it structurally impossible for the solver to even understand the code. It maximizes its reward by getting 0 to 0 without requiring any real complexity.
So we're not just worried about the AI learning to code, we're worried about the AI learning to game its own training environment, which would make it useless for actual production software. If the challenger becomes too smart, it can exploit the rules of the adversarial game itself, and the whole training becomes pointless.
The paper explicitly states that it seems hard to theoretically prevent this kind of behavior as long as the challenger has a Turing-complete action space, meaning it can write any code it can imagine. This really changes how we have to think about self-play in these open domains.
It's not like Go.
It's not like Go where the rules are fixed and robust. Here, the agent can mess with the rule engine itself.
So what's the mitigation strategy? What did SSR adopt to manage this existential risk?
The key is not to pursue this deep, unrestricted self-play that tries to fully explore the game rules. Instead, SSR's success relies on keeping the self-play shallower and, critically, grounded in large, diverse, real-world data.
How does that help?
The goal is to constrain the AI by its instructions, those removal-oriented and history-aware prompts we talked about. They act as guide rails to prevent the agent from collapsing into the dominant strategy of creating trivial, synthetic, or impossible problems. The learning is constrained by the real physics of the code repositories it's interacting with.
It's essentially using the constraints of the real world, the fact that code has to compile, tests have to run, patches have to apply, to prevent the AI from disappearing down some theoretical, non-useful rabbit hole of dominant strategies.
Exactly. The real world provides the guardrails.
The theoretical risks are clearly high, but the empirical results demonstrate that SSR managed to successfully navigate that adversarial landscape. So let's look at the numbers. Does SSR actually beat the agents that were trained on that high-quality, human-curated data?
It does, and consistently so, which is really the most exciting takeaway from all this. SSR achieved steady self-improvement throughout its entire training. The core comparison they make is against a very robust baseline RL approach. This baseline was trained on the exact same environments with the same hyperparameters as SSR, but the baseline received the standard human-authored issue descriptions and test suites, the gold standard of conventional human data.
So the human data baseline is essentially a state-of-the-art RL agent, just trained in the conventional way. What were the specific quantifiable gains when you compared SSR to that?
SSR showed really significant quantifiable gains. I mean, it moved the needle in a field where even tiny incremental improvements are usually a huge achievement. On the highly verified and robust SWE-bench Verified benchmark, the final SSR model outperformed that human data baseline by an astonishing plus 10.4 points.
10 points. That's huge.
It's huge. And then when they tested it on the more complex and realistic SWE-bench Pro benchmark, which has a wider variety of harder multi-step issues, SSR still saw an improvement of plus 7.8 points.
That is a massive margin in this field. It really suggests that these self-generated training signals, when they're grounded in real code bases and designed to be maximally challenging, are just objectively richer and more effective than relying on human engineering and curation.
The AI is a better teacher to itself than we are.
It seems so.
And what's really important is that the agents were evaluated on natural language issues on these benchmarks, issues that were completely absent from the self-play training loop. So the improvement is purely from learning better coding and debugging skills, not from getting better at understanding natural language issues.
So the improvement is fundamentally about code capability, not language understanding.
Exactly.
Now, to understand why this works so well, the researchers did some important ablation studies where they pulled apart the different components of self-play. What did they learn about the value of that joint learning process?
They compared the full self-play framework against two other variants, repair-only and injection-only. Repair-only trained the solver exclusively on bugs that were collected from early self-play iterations, but it didn't do any new, online dynamic bug generation. Injection only trained the bug generator, but it lacked the training signal that comes from the success and failure of the repair attempts.
And I'm guessing the result confirms the wisdom of the full adversarial approach.
Full self-play was unambiguously the best performer, by a long shot. The repair-only variant was significantly inferior because it lacked that dynamic, evolving task distribution you get from online self-play. It just quickly ran out of structurally new things to learn.
Right, so the first batch of self-generated bugs might be simple things like typos or function removals. Once the solver masters those initial failure modes, its training just plateaus because it stops seeing problems that truly challenge its semantic understanding of the codebase.
Exactly. It confirms that the continuous push from the challenger is the core driver of progress.
And what about the injection-only variant?
That training actually degraded performance. It was worse than the baseline, which confirms that just generating bugs isn't enough. The model has to also get the feedback from the success and failure of solving them.
This suggests that the process of generating a quality bug, identifying the tests, breaking the functionality in a meaningful way, weakening the test, that whole process is itself a substantial and necessary part of the learning. The challenger learns about the constraints of the system by trying to break it in a verifiable way.
You're absolutely right. It's a fundamental lesson. The self-play dynamic teaches both sides at the same time. It enables the policy to understand code from both the destructive and the constructive viewpoints. It learns the geometry of the bug, where errors hide, and what makes them easy or hard to find.
They also analyze the optimal bug injection strategies. We talked about the removal-oriented and the history-aware strategies. How did guiding the injection process actually impact the results?
The naive direct injection approach, which was just simple prompting without any detailed guidance, it performed the worst. It tended to collapse into these superficial, trivial one-line bugs that offered very little training signal.
Like changing a variable assignment from true to false in some non-critical part of the code?
Exactly. So without those guardrails we talked about, the AI just defaults to the easiest possible path to satisfy the minimum requirements for a valid bug artifact.
Makes sense.
The removal-only strategy generated stronger bugs by forcing reconstruction, and that yielded better results. But the best overall performance came from combining removal plus history. Leveraging historical changes like reverting past fixes incorporated more realistic and diverse bug patterns, and that maximized the challenge and the instruction for the solver.
So confirms that guiding the AI to look at real complexity, even if it's self-generated, is the key.
It is.
Finally, what about the reward mechanism itself? Did that complex adversarial solve rate feedback, the penalty for CEDOs being 0, or 1? Did it make a big difference? I mean, this is a meticulously engineered component.
Surprisingly, no. The ablation study found that providing that explicit solve rate feedback to the injector only provided a slight and largely negligible advantage over just giving the injector a simple binary reward based on whether the bug passed its consistency checks.
That's fascinating. Why do you think that is? If the incentive structure is so carefully designed to target that sweet spot of difficulty, why didn't it pay off more?
The researchers hypothesized that the feedback signal is just too weak and too noisy. For the bug injector, trying to infer all the many factors that led to a specific solve rate, $6, from just a few noisy solver attempts, is inherently very difficult. And crucially, the primary benefit of the evolving curriculum comes not from that scalar feedback, but from the fact that both roles share an evolving policy.
Ah, right, the shared weights.
Exactly. The underlying policy is continually getting better at fixing bugs, and because the injector shares those same weights, it naturally becomes better at generating challenging bugs that test the current policy. It automatically tracks the solver's frontier of capability without needing that explicit feedback on the solve rate.
So the shared learning is the real driving force, not the nuanced reward function.
That seems to be the case.
SSR is clearly a landmark step. It proves that self-play is viable in these open software domains.
Right.
But the research documentation is also very transparent about its limitations and the challenges that still remain before we get to true superintelligence. So let's look at the current constraints of the framework.
Yeah, the framework still relies very heavily on the verification oracle being unit tests, and that really limits the scope of problems that SSR can tackle.
Right.
Real-world software engineering is vast. It includes architecture decisions, performance bottlenecks, major version migrations, security vulnerabilities, large-scale feature integration. Unit tests only capture a small, very specific subset of what correctness means.
So for true superintelligence, we need verification against much higher-level goals. Maybe something aligned with efforts like Code Clash, which defines success based on achieving a big objective like migrating a whole codebase from Python 2 to Python 3 rather than just passing a predefined test suite.
Absolutely. We need a way to reward these long horizon complex goals. Another constraint is the issue of hidden oracles, or maybe the lack thereof. Right now, the solver is provided with the complete oracle. It gets the reverse test weakening patch, which explicitly tells it what tests have to pass.
And the risk there is overfitting, right?
Precisely. This design could theoretically enable the agent to develop reward hacking behaviors, like overfitting to that specific set of tests rather than developing a genuine, robust bug-fixing capability that works on code it's never seen before.
So future versions would probably need to enforce private and public test splits.
Right, to mimic real development where you have some tests you can see, but the ultimate success depends on passing unseen validation tests later on.
Beyond these design constraints, the team was also really transparent about key unsuccessful attempts during their research, which tell us a lot about the current limits of LLMs in this space. What was the major practical setback they ran into?
One of the major failures was their attempt to generate natural language issue descriptions. SSR has to rely on that formal test specification for its curriculum because their initial attempts to generate a human-readable issue description. They just failed consistently.
What did they look like?
The descriptions were often incoherent, illogical, or they just copied the test patch verbatim and put it into English sentences.
That is a crucial lesson. It shows that while LLMs are mastering logic and code manipulation, the process of distilling that logic back into coherent, accurate human communication, basically writing a good bug report, that remains an unsolved problem.
For now, at least. Formal specification, it turns out, is a much more robust training signal than human language.
It speaks volumes about the current limitations of instruction tuning and the inherent noise in free-form language generation when the output has to be logically sound and factually accurate.
It does.
And the second major bottleneck was a crucial practical limitation regarding scale, one that prevented the authors from pushing SSR even further.
Yes. The biggest technical challenge was training instability. Even when they were following state-of-the-art practices for RL training, they observed instability that would manifest as just gibberish outputs, or the model would get stuck in a loop of repetitive, useless actions.
And what do they think causes that?
They hypothesize it stems from the combination of these really long horizon rollouts, suboptimal hyperparameters, and just the intrinsic complexity of managing the self-play dynamic across a massive code environment.
So addressing that instability is the key to unlocking the full potential of SSR. If the process keeps falling over, you can't run the millions of self-play steps you would need to reach superhuman capability.
It is the ultimate bottleneck for applying this powerful theoretical approach at industrial scale.
Okay, so what does this all mean for the field's future? We've seen SSR succeed at continuous self-improvement in bug fixing. Where does the next evolution take us in terms of agent capability?
The future has to move beyond simple bug fixing to the synthesis of complex multi-step tasks. Right now, SSR is excellent at short horizon tasks, identifying a bug, applying a patch, all within a single session.
Right.
But real engineering involves long horizon, complex workflows, major version migrations, refactoring huge sections of a code base, or building new software stacks from scratch over multiple days, even weeks of work.
And how do we even tackle those massive multi-session tasks using RL? It seems impossible.
The current reinforcement learning approach is inherently inefficient for these tasks. You're faced with an intractable credit assignment problem. Imagine you run a massive migration workflow that spans thousands of decisions. You get a sparse terminal reward. You get +1 if you finish the entire migration successfully 10,000 steps later.
And -1 if you fail at step 9,999 because of minor error you made way back at the beginning.
Exactly. That sparse feedback makes it impossible for the agent to know which of those 9,999 steps contributed to the failure.
So what's the path forward?
Future work is going to require new training paradigms. We need things that can exploit the asymmetry between generation and verification, allowing for robust self-verification at intermediate stages. We need ways to deliver dense, structured feedback beyond just a single scalar reward. We'll need mechanisms to manage the massive context required for long-term project memory, maybe using multi-context rollouts or automated context compaction.
So SSR has shown that the core self-training loop works. Now we just need the scaffolding to make that loop run reliably for months instead of minutes.
That's a great way to put it.
What an incredible deep dive into self-play SWE-RL. We've really seen how this novel approach uses these adversarial roles, the challenger injecting complex, hidden bugs, and the solver repairing them, to create a continuous, self-improving agent. an agent that is already outperforming models that were painstakingly trained on costly human-curated data.
Yeah.
The AI, in effect, has cut the cord and is designing its own high-difficulty education.
SSR is more than just an incrementally better training method. I think it's a paradigm shift toward genuinely autonomous agents. It shows that by grounding self-play in real code bases, and by meticulously managing that competitive tension between the challenger and the solver, we can actually bypass the fundamental human data ceiling that has limited agent scalability until now.
And for anyone who uses these AI tools daily, this fundamentally changes our understanding of how these systems are trained and what their ultimate ceiling might even be.
The era of the self-taught AI developer, it's really beginning right now.
Absolutely. The data speaks for itself. I mean, those +10 and +7 point games, that's a loud signal that synthetic evolving difficulty, when you constrain it with the physics of real code, it just beats hand-curated realism. This new training paradigm changes the game entirely.
And this brings us right back to the most critical conceptual challenge we talked about. The need to prevent the challenger from using those dominant strategies, from finding the cheat codes of the adversarial game.
Right.
As we build agents that are capable of superintelligence, the most crucial engineering challenge might shift from just creating more powerful base LLM models to meticulously designing the rules of the game, the adversarial training environment itself.
It's a question of governance and alignment, but you're implementing it directly in the training infrastructure. You have to ask, will the AI learn genuine complexity and utility that actually benefits us, or will it just find the easiest path to superficial success and game its own reward function?
That's the thought I really want to leave you with. The success of a model like SSR depends entirely on its structural constraints. So the question becomes, what rules will we set for the AIs that eventually design and maintain the foundation of all of our software? The design of the sandbox really determines the fate of the developer inside it.